Welcome to our lesson on series and parallel circuits. When you flip a switch in an electric circuit, you are completing the pathway for the electrons to travel from the power source to the appliance. As the electrons pass through the resistor, they transfer electrical energy to the resistor and then return to the power source to be re-energized. Here's a typical circuit. It contains a power source, a switch, and a resistor. However, many circuits contain more than one resistor. In this particular situation, we have put three resistors in series with each other. These resistors can be replaced consecutively along a single pathway so that each resistor has access to every electron in the circuit. This is known as a series circuit. Electrons must travel through each of the three resistors and then return to the battery. Another method of connecting resistors is by connecting them in parallel. Here we have the start of a circuit. Instead of placing the resistors along the same pathway as the first resistor, we place them along bridges. Each resistor is placed on a separate pathway along the circuit so that each resistor has access to only a limited number of electrons. This is known as a parallel circuit. There's one resistor in parallel. These two resistors are now in parallel with each other because electrons coming from the battery can either go from this point, they can go down, or they can go across. Let's add another resistor in parallel. And here we have a third resistor. These three resistors are in parallel with each other. Electrons can go through one of three pathways. The first pathway, the second, and the third possible route for these electrons. Because of this, each electron has a complete voltage drop across each resistor. Because the electrons come from the battery, the only pathway they take is through the resistor, then back to the battery. So they give a complete voltage drop across this resistor. The electrons that choose to go through the next resistor likewise give off that same amount of voltage. Because the pathways for electrons are different for series and parallel circuits, the total resistance for each type of circuit is determined using different methods. In the mid-1800s, Kirchhoff used the conservation of energy and conservation of charge laws to develop his voltage and current laws. We use these to calculate total resistance for both series and parallel circuits. For series circuits, Kirchhoff found that the current was constant through each resistor in the circuit, and the potential difference, the voltage drop across each resistor, could be added to equal the original potential difference of the power source. So, as electrons pass through each of these three resistors, the voltage drop across those three resistors, numbers 1, 2, and 3, is going to add to the total voltage of the battery. However, the current that goes through this resistor has to be the same as the current through each of the other two resistors because the current or flow of electrons has no other pathway to take. Kirchhoff found that the total resistance is equal to the sum of the resistance of these three resistors. Numbers 1, 2, and 3, and as you can see, electrons must pass through all three resistors before returning to the battery. So this is the situation for series circuits. For parallel circuits, Kirchhoff found that the potential different drops were constant through each resistor, and the current through each resistor could be added to equal the total current of the circuit. In this particular setup, we have three resistors in parallel. As electrons leave the battery, some of them can go through resistor number 1. Some of them can go through 2. Some of them can go through 3. Each electron that goes through resistor number 1 is going to give its complete voltage drop to this single resistor. Therefore, the voltage drops across each of the 3 resistors is considered to be also equal to the total voltage of the power source. However, the current, since some electrons at this point, some can go down through resistor number 1 and some can go across to resistors number 2 and 3, the total current coming from the battery is equal to the sum of how much goes through number 1 plus the current through number 2 plus the current through number 3. Kirchhoff found that the total resistance of the circuit is much different than in series. Here you have to take the inverse of the first resistor plus the inverse of the second plus the inverse of the third will give you an answer which is the inverse of the total resistance. The more resistors you put into a parallel circuit, the less resistance you have as a total. Whereas with series, the more resistors you put into series, the higher the total resistance. At this point, some of the electrons can go through resistor number 1, some through number 2, and some through number 3. Some circuits may require a combination of both series and parallel as shown in the diagram. Here we have resistor number 1, which is in series with resistors numbers 2 and 3. Electrons leaving the battery must go through X, and therefore all must go through resistor number 1. However, at point Y, resistors can either go down through number 2 or over and through number 3, then coming back to point Z, reuniting and going back to the battery. In the above circuit, resistors 2 and 3 are in parallel with each other, and both are in series with resistor number 1. As we mentioned, between points X and Y, the voltage drops due to resistor 1. Between points Y and Z, the current splits so that some will flow through resistor number 2 and some will flow through resistor 3. However, at point Y, please remember that the voltage at this point is the same whether they go through resistor number 2 or resistor number 3. The total resistance of the circuit is found using the following equation. The combination, the total resistance, is equal to resistor number 1, which is in series, so it's added, to resistors number 2 and 3, which are in parallel with each other. Therefore, we find their total parallel resistance, then add it as a series to resistor number 1. In summary, Ohm's law gives us V is equal to IR, and when solved for current, gives I is equal to V over R. If we can use Kirchhoff's laws to determine the total resistance of a circuit, and we know the total voltage, then we can predict the current through the complete circuit or through parts of the circuit. Here are Kirchhoff's resistance laws for series, parallel, and a combination series-parallel circuit. Once resistance is determined, then that resistance allows us to predict current using a constant voltage and Ohm's law. The next lesson will show examples of these three types of circuits: a simple series circuit, a parallel circuit, and a combination circuit.